Section 16.5 is where we finally start to deal quantitatively with weak acids and weak bases. So just to remind you, weak acids and weak bases are those that will reach equilibrium when they react with water. So we can take something like HNO2 plus H2O, and this will reach equilibrium, forming H3O plus and the nitrite ion. That's an example of a weak acid. And let's do the prototypical weak base reaction, ammonia with water. That will also reach equilibrium, giving us NH4 plus plus OH minus. Now we can write equilibrium expressions for these types of reactions. Water is liquid, and so it will not be present in these equilibrium expressions. And here we end up with H3O plus, NO2 minus, over H NO2. And here we end up with a K equal to OH minus, NH4 plus, and NH3. And these equilibrium constants are special because they relate to the acidity or the basicity of nitrous acid and ammonia. So we will call these Ka values, the equilibrium constant for the reaction of nitrous acid with water, or Kb values, the equilibrium constant for the reaction of ammonia or any base with water. And these follow a similar form. I could take nitrous acid and replace it with any other acid, and it would take this same form of H3O plus and A minus on the top and HA on the bottom. And when you get into polyprotic acids, we've talked a little bit about how like HPO4 2 minus can actually act as an acid despite having a charge of 2 minus. Well, we'd have to, I suppose, modify the charges here a little bit, but it would follow the same idea. If HPO4 2 minus is acting like an acid, then the Ka value for HPO4 minus would be H3O plus PO4 3 minus over HPO4 2 minus. And so the difference is we've removed a hydrogen and we've increased the negative charge by 1. Okay, and for bases, the Kb value is always going to be OH minus, and then we'll call this HB and B minus. And again, with the charges here, everything depends on the particular context. Like ammonia, for example, it has a positively charged conjugate acid and it is itself neutral. Well, most of our bases are going to be anions. They're going to be negatively charged, so this is maybe a better generic representation of how these will look. But you will always have the OH minus and then your base with 1 hydrogen gained and a charge that's 1 greater than it used to be. So these are the Ka and the Kb values, and we've already had a whole chapter on how to solve ice tables for reactions that involve equilibrium. So really, I'm not even introducing anything new at all, and we can dive right into solving these sorts of equations. I do want to add one thing though. So your Ka values will range widely in their values. Just like H3O plus concentration ranges over many, many orders of magnitude, and it becomes convenient to talk about something like the pH, the negative log of the H3O plus concentration, we'll also sometimes talk about the pKa, which is the negative log of the Ka. And we'll occasionally talk about the pKb, which is equal to the negative log of the Kb value. Now this might seem a little bit silly now, but I promise you pKa values will be extremely useful later on. So let's leave that, and let's just solve a couple of practice problems. Okay, so if I have, and one more thing to note. When we're talking about acids and bases, we will be using a new unit of concentration, and that is the formal concentration. And the formal concentration is just the number of formula units per liter. And the distinction between the formal concentration and the molar concentration is that the formal concentration is an abstract concentration of an acid or base before it undergoes its acid-base reaction. And so that's my little bit of an introduction, and then let's give you a particular example. Okay, so if I have nitrous acid, I should have just left it up here, HNO2 plus H2O in equilibrium with H3O plus NO2 minus. And the question is, if I have 0.250 formal concentration of nitrous acid, what will be the pH? Well, we know that HNO2 is going to react with water, and so if I write my ice table, I'm going to start with 0.250 molar HNO2. We'll set these starting at values of 0. There's going to be a minus x, plus x, and plus x. So we'll have x, and we'll have 0.250 minus x is the molar concentration of HNO2. So do I really have a 0.250 molar solution of nitrous acid? No, it's something less than that, and we don't even know what the value is less than that. So for people that are really pedantic and want to be very precise with their language, which I sometimes am, we'll say that this is a 0.250 formal solution of nitrous acid. And that means that the initial concentration here is 0.250, and we don't even know yet what the molar concentration is. It's probably pretty close to 0.250, but it's certainly at least a little bit lower than 0.250, and so just to be really obsessively precise, we'll call it a 0.250 formal concentration. Okay, so you don't really, for you, if you see an F, you can just say, well, that's basically the molar concentration at the that I'm going to use in my ice table, and you don't have to overthink it too much. All right, so we need a Ka value for nitrous acid. So the Ka is equal to 4.0 times 10 to the negative fourth. And that is going to equal x squared over 0.250 minus x. And 4.0 times 10 to the negative fourth is a small enough Ka value that I'm at least going to hope that that x is small enough to ignore, and that would mean that x squared is equal to 4.0 times 10 to the negative fourth times 0.25. Well, let's calculate that, find a value for x, and check whether we're justified in making that simplification. So, I mean, ultimately we're going to take the square root then of that product. The square root of 4e negative 4 times 0.25, and we get 0.01. Now, is that small enough? Well, we'll take 0.01, we'll divide it by that initial concentration of 0.25, multiply by 100, and what we're looking for is this change value, the value of x, to be less than or equal to 5%. And it looks like it's 4%, so we're just barely scraping by, but that's good enough, and we can go ahead and move onward. So x equals 0.01, and oh, was that right? Sorry, I'm suddenly second guessing myself. Oh yeah, sorry, it was 0.01. And then we can start to put that in. 0.250 minus 0.01. Well, now we know it's actually 0.240 molar. And we know these concentrations, 0.01 molar, and this concentration, 0.01 molar. And the pH is going to equal the negative log of the H3O plus concentration, and in this case that will be a 2, because this is 10 to the negative second power. I can prove that just in case you want to double check. Okay, so we'll do the negative base 10 log of 0.01. And we get 2.0. And actually, it looks like we have 3 significant figures from the concentration, but only 2 significant figures from our Ka value. So we get 2.00 to give us the proper number of significant figures. Okay, that's a pretty easy equilibrium problem. And all of our acid-base problems are going to follow this pattern, or I should say the overwhelming majority of them will follow this pattern, where we have the K value is equal to x squared over the initial concentration minus x. You try to neglect the x. If you can, then it's a really easy, straightforward problem. So let's look at a base. Bases are just going to have one slight difference. And the example we have is a 0.325 formal solution of pyridine. And you know, I don't even know the chemical formula for pyridine off the top of my head, and I don't need to look it up. That's the great thing about how these all follow patterns. So I'll show you how you have a Dr. Rowley approved style of sloppiness that you can apply in these sorts of problems. Okay, so we have a Kb equal to 1.7 times 10 to the negative 9th. And so pyridine, like I said, I don't even know what its formula is, but I can just say B plus, I'll say B minus plus H2O is in equilibrium with HB plus OH minus. You see that? I don't really need to know the chemical formula for pyridine in order to write an equation which is going to be good enough for our ice table. Isn't that neat? So we're going to start off with none of the conjugate acid and no hydroxide. 0.325 molar of the pyridine, minus x plus x plus x, 0.325 minus x, x, and x. And we'll put our Kb value, 1.7 times 10 to the negative 9th, equal to x squared over 0.325 minus x. Now this times 10 to the negative 9th, that x is definitely going to be a small number. And we can prove that after the fact, but I'm not too concerned about having to use the quadratic formula here. So we'll pull up, here, let me get my head out of the way of the formula. There we go. Okay, we'll pull up the calculator. I have 1.7 times 10 to the negative 9th times 0.325. And actually I'm going to go back and I'm just going to square root this straight away. So the square root of that product. And I get a value x is equal to 2.35 times 10 to the negative 5th. Okay, now if we wanted to, we could take 2.35 times 10 to the negative 5th and divide it by that initial concentration, 0.325 times 100%, and we see, are we at or below 5%? Well, it looks like we're at about 0.07 of a percent, and so that approximation was very valid. And 0.325 minus 2 times 10 to the negative 5th, it's not even going to affect that number. And then we can just put x in for these values. 2.35 times 10 to the negative 5th. These are now molar concentrations. 2.35 times 10 to the negative 5th. Okay, well now you have a couple of options for getting to our final goal, which is the pH of the solution. We have the OH minus concentration instead of the H3O plus concentration. So you cannot just take the negative base 10 log and be done with it. That would give you the POH. So the POH is equal to the negative base 10 log of the OH minus concentration. But the pH is equal to 14 minus the POH. And what I like to do is combine these two together. And so the pH is equal to 14 minus the negative log of the OH. So that'll actually end up being a 14 plus the log of the OH minus concentration. And I just think that's the quickest, easiest, neatest way to get the pH from ice table involving a base. Alternatively, you could take this and find the H3O plus concentration, because H3O plus concentration times OH minus concentration is equal to Kw, or 10 to the negative 14th. And then from there take the negative log of that value. But I think this is pretty slick. I like to do it this way. So let's figure out the pH. I'm going to say 14 plus the log of 2.35 times 10 to the negative 5th. I type that in right. And I get a pH of 9.37. pH is equal to 9.37. We only get 2 sig figs because our Kb value limited us to 2 sig figs all the way back there. So now you can look at, there's a table in your book, table 16.2, that shows a whole bunch of Ka and Kb values. And then also there is an appendix which shows even more. And so now you can take any weak acid or weak base problem that we give you and find the Ka or the Kb value from the appendix or from one of those tables if it happens to be on the table, and find the pH. Now, there are a couple of useful relations that I want to introduce right now that don't come up until a little bit later in your textbook. And one of them is that for conjugate acid-base pairs, we can relate the strength of the Ka value for the acid and the Kb value of the base. And let's just think about it here. Let's take the Ka times the Kb. And if these are an acid-base pair, then the Ka is going to be H3O plus times A minus over HA. Right? And if these are a conjugate acid-base pair, then this is the base and that is the acid. Maybe, in fact, maybe it would be better to write it this way. Oh, sorry. We'll say this is the conjugate base and this is the conjugate acid. Is that fair? That way is really generic and I think clear what we mean. These are for a conjugate acid-base pair, then we're going to have OH minus times the conjugate acid over the conjugate base. That's the Kb value. So we have Ka and Kb. And you'll notice we get a lot of cancellations. All we're left with is H3O plus and OH minus. And what is that? That is Kw. And so if I know the Ka value, I can find the Kb value for its conjugate base by taking 10 to the negative 14th and dividing by the Ka value. And likewise, if I know the Kb value of a base, I can find the Ka of its conjugate by taking Kw divided by the Kb value. And this only works for conjugate acid-base pairs because this acid and that acid are the very same thing in the case of a conjugate pair. Ka times Kb equals Kw. And then I also like this one. This one doesn't appear in your textbook at all, but I think it's worth looking at. For reaction partners. Okay, let's put up a hypothetical here. Let's react nitrous acid plus ammonia. Nitrous acid plus ammonia. And that's going to form NH4 plus NO2 minus. Okay, this is an acid-base reaction that doesn't involve water, and the K for this reaction is not a Ka or a Kb. There's no water, there's no H3O plus, there's no OH minus, and so this K is going to equal NH4 plus NO2 minus over HNO2 and NH3. Well, it would be nice if we could get an idea for like what is the value of K? Is it going to be product favored or reactant favored? Is there any way we can figure this out? And the answer is yes. There's a great simple way to look at this. What I have here, I should have written it the other way. That's all right. I have NH4 plus over NH3. What does that look like? Well, that looks an awful lot like the Kb for ammonia. What's it missing? It's missing the OH minus in the numerator. So what it really is the Kb divided by the OH minus concentration. Is that fair? And then here we have nitrite ion over nitrous acid. Well, that looks an awful lot like the Ka. I'll put this is the Kb for NH3 and the Ka for HNO2. That looks an awful lot like the Ka, nitrite ion over nitrous acid. What's it missing? The H3O plus in the numerator. So what we really have is Ka divided by H3O plus. Well, and now what we have is Kb times Ka over Kw. And we can not only get a general idea for whether this is product favored or reactant favored, we can actually get a value for K, for the equilibrium constant here. Because I can look up the Kb for ammonia, I can look up the Ka for nitrous acid, and divide it by Kw to get a value for whether this lies toward products or lies toward reactants. And I think that's pretty neat. So that's actually going to end it for our weak acids and bases section. Of course, we'll be revisiting these ideas in both the quiz and building on them in future sections.